Anybody have any open questions before we get started? Anybody have anything, any issues or any concerns they want to address? Yes.
Why can't you like define like classes? Like instead of like making like a class, why can't you like make something inside of an object? Yeah, like.
Why not make something inside of an object instead of creating a class? So why do we create classes? So the classes are going to let us create many objects of the same type. So for example, there's an int class in Scala, and that lets us have all kinds of different integers throughout our code. So we can have integers, variables of type integer, all over with all different values. If we had that inside of an object, we would only be able to have one of them. We would only be able to have one int in our program, and then that would be it. So an object, there can only be one of them, but class says we can create many, many objects of this type by saying new this, new this, new this. So like in our example last time, we wanted multiple players. We want a multiplayer game. We're going to create a player class and then be able to have as many players in our game as we want. Does that answer your question?
Yeah.
Okay. Anything else? Anybody have anything? Oh, yeah, we do. I need to sub for Prime for Twitch lecture chat? Yeah, you do. You can just pay me. Just slip your money under my office door. I'll make sure Twitch gets it. So is the AO expected deadline due next week or the hard deadline? So there's only one deadline for application objectives, which will be next Wednesday, but let me just absolutely make sure. So I do not want to misspeak here. Which will be next week. So the application deadline is always on the actual deadline of task 3 for that homework. So this is it. That's one deadline. That's your shot at that. There's no early deadline and late deadline, because that doesn't make sense to get an early deadline or an expected deadline on an application objective. How would that factor into things? The application objective is straight up a whole application objective. It's not working your way towards an application objective. It's always due for the project on the task 3 deadline, not the task 3 expected deadline, which was today. No, wait. Yeah, today. It is the task 2 actual deadline today, task 3 expected deadline this morning. So next week, when task 3 is like legit due, like holy crap, it's due, that's when the application deadline is. And that's all or nothing. Get it by this time, and you're good. So the idea is that you're meeting the expected deadlines of all the tasks, and then after task 3, you have kind of a week to do the application objective. I know you're also working on project 2, task 1. So ideally, you're working on the application objective throughout the project and getting it done. But yeah, that's due next Wednesday morning is project 1 application objective. Yeah, and all application objectives are optional to improve your grade. All right, anything else? We got some good questions out of that. I'm glad we took some time. Okay, so I want to go back to some slides that I didn't get to last week. This is last week's Wednesday slides, if you're looking at the course website and you want to download them and look through them yourself. Model of execution. I'll go through these fairly quick. A lot of this is kind of high-level knowledge that you won't directly be tested on, but it's all good stuff to know. And towards the end, I'll talk about the stack a little bit, which is stuff that I expect you to already know at this point, but we'll cover it more formally. So interpretation versus compilation. So interpretation, if your code is interpreted, this means you have an interpreter running through, reading line by line, and executing your code. This kind of feels like what all our code is doing. It feels like code is interpreted. It just gets ran line by line. But there's a big difference between interpretation, which would be your JavaScript and your Python last semester, and compilation, which is our Scala this semester. Compilation, Scala is a compiled language. Scala is going to be completely translated into another language before it runs. So when you compile Scala or any compiled language, when you compile it, you're taking it, your source code is read. The entire code for your whole project is read, parsed, translated into another language, and then when you run your program, the code in that translated language is then interpreted when it's executed. So there's an extra step. We can't just run our code. We have this compilation process. You can feel this in IntelliJ. You hit the green go button and you want that thing to go. But instead there's a progress bar in the bottom. It takes a while, especially like the examples repo. The entire project is being compiled, being translated to another language, and then it runs. So there's 2 steps to the running process here, compile and then run. That's why you're seeing compilation errors instead of runtime errors this semester, which you may or may not feel the difference of those. But it's definitely why your program takes a while to run. That's the compilation time. Where your Python and JavaScript programs, they just run, baby. You run the interpreter, and it goes right to line 1 of your main method, or line 1 of your script, and it just starts running things immediately. We have to wait for compilation here. So we tend to get different types of errors, which I don't know how obvious the difference is out there, but we do get different types of errors. We get compilation errors instead of runtime errors, and I want to talk about the difference between the two. So this will be a runtime error in Python. We're going to get a runtime error when we run this code on the right. So at this point, I would expect you to be able to stare at these for a little while and spot the error. I'll just tell you because we got some stuff to go through. But for what it's worth, this is how you define a class in Python. We're going to define a method named init, which is going to be the constructor. It's not up in the line up here like it is in Scala. And we have very explicitly a variable named self, which is the same as this in Scala. Python says, let's be very clear about what's happening. There is an extra parameter. It's a reference to the calling object. Let's make it clear. It's right there, and you have to type this. If you don't type self in Python, it's going to yell at you. Things are going to break. So it makes it explicit. So I'm going to create an instance of this object. I'm going to call this add to state method. It's going to add to the state variable, which is going to be of type int, because I gave it 5 as an int. Python, we don't specify our types, but we do have to keep track of them. And then I'm going to add 10 to that. So I'm going to have state, which is 5 at this point, and then add 10 to it, and then print 15 to the screen. Yay, go us. The program on the right is going to do the same thing but have a runtime error. Instead of 10 as an int, I'm going to use 10 as a string. And now when we get to this line right here, we're adding 5 the int and 10 the string. These types are not compatible. We can't add them, and we're going to get an error at this point. You saw this a lot last semester. If you took 115 here, you did this a lot in Python. You would have type errors, especially when you're printing things to the screen. The value of my int is, and then plus, and then your int. And it says string and int incompatible. I can't add these things together. You have to put str and then your int, convert it to a string, and then concatenate them together. It's a frustrating thing with Python that we all have to deal with. It won't auto-convert when you print out an int like that or concatenate strings. So this is going to give us an error. But the important thing here is that the program on the right still runs. This program runs, and it will even get to this line and print adding to state to the screen. It will run, and then during runtime, while your code is running, that's what we mean by a runtime error, while your code is running, you will get this error, your program crashes, and nothing else runs. So we print this line, but we never get to this line because our program crashed when we got right here. That's a runtime error. You're going to see those a lot when you code in Python and JavaScript. This is probably the most common error you're going to see in those languages. Runtime errors. Your program's running, it came across something it couldn't do, and then it crashed. In Scala, with the same idea, the same code, we're going to get what's called a compilation error. With a compilation error, Scala is going to look at all the types. It's going to find that type mismatch right away because we have a strongly typed compiled language. And it's going to say right here, hey, you have an int. Oh, right here. It's going to say this method takes an int. You're giving it a string. expected int, found string, wrong types, and it doesn't even run. Nothing will run here. Scala's just going to say, I'm not happy with your code. Fix your code before I do anything at all. So this is a compilation error. This line is never printed to the screen. We never get to that line because during the compilation process, when your Scala code is being translated into another language, during that process, this error was found, the type mismatch, expected int, found string. The compilation process can't finish, so it never gets to the point where that code that you're translating into is able to be interpreted. So nothing runs. You never run a single line of code. This doesn't print to the screen. This certainly doesn't print to the screen. Nothing happens at all. So this is the type of error we usually see in Scala or any compiled language is the compilation errors. And IntelliJ is pretty good about giving us red underlines under our compilation errors and saying, hey, fix this so I can run your program. So these are the kind of errors that we see in these compiled languages. Nothing even runs. Nothing happens at all. For what it's worth, I like compiler errors better than runtime errors. Runtime errors can be scary because what if you have a runtime error inside an else statement, but during testing you only hit the if block of that statement, and then you release the code, it's tested, you think it's good, but you forgot to write a test case that hits the else, and then out in production, your user, very first thing they do, they hit that else, program crashes, oh crap, we're in trouble. With compilation errors, the compiler will find all kinds of bugs for you before it even lets you run the program. So by the time you get to running the program, you got most of the bugs that will crash your program at least out of the way already before you can even run anything. So it really helps you find and eradicate those bugs early on in the development process instead of literally while your program is running. That's like the last line of defense. We already lost the battle if we get to that point. The language that Scala is compiled into is Java bytecode. This is the same language that Java code is compiled into. If you write a program in Java, you compile it. It's compiling to Java bytecode. So Scala code and Java code after compilation looks identical, at least to the JVM, at least to the JVM, which is the interpreter that's running Java bytecode. This code looks the same. Java, you've probably seen these pop-ups from time to time. Whenever you see that pop-up, that means you have the JVM installed on your machine, on your device, which means that device can run Java bytecode. So if you compile your Scala code on that device, you can just run your Scala code on that JVM. So very handy. It lets Scala borrow a lot from Java, a lot of the architecture and infrastructure for Java. Scala just piggybacks on that and gives us some nicer notation and stuff to be able to work with. So for example, I don't know if we saw it this semester. I don't think I showed it. But if you do math with a capital M dot whatever, that's actually a Java library. And we'll actually use quite a bit of Java code in our Scala programs. Most notably, there are GUIs. We're using JavaFX. It's a Java library, and we'll use a ScalaFX wrapper around that library to add a few Scala features to it. But we'll use a lot of Java code when we write our Scala programs because we're using compiled libraries that are already in Java bytecode, and we just can use those as much as we want. We can mix Java code and Scala code as much as we want. And we won't do that in this class, but it's something, aside from libraries. But you could actually write a Java class and a Scala class in the same package, compile them both, everything's fine. Everything works interoperably. So we will use some Java libraries. The math, capital M, math dot, it's a Java library. If you use a lowercase m, it's the Scala version of that library. All right. Any questions on interpretation and compilation? It's a fun topic, but we just don't have the time to really dive into it. But if anybody's got questions. Yeah.
So it gets translated into Java bytecode.
Mm-hmm.
Does it ever get translated to anything lower than that? Or is that?
Kinda. So it gets translated to Java bytecode. Does it get translated to anything farther than that. It doesn't really get translated to something, depending on how you look at it, something lower than that. But that's what the interpreter is doing. It'll take, the node. Let me back up. An interpreter for JavaScript, an interpreter for Python, interpreter for Java bytecode. Any of those interpreters, what they're doing is taking that code and translating them into machine code to be able to execute. So during that process, it kind of is translated to another language, but not wholesale like a compiler does. Like takes this whole thing and compiles it over here. But an interpreter is going to take that line of code, convert it into machine code, which is what your CPU or GPU understands. The actual bit level instructions that are hard coded into your hardware, that are built into your hardware. That's what the JVM is going to do. It takes your Java bytecode, turns it into ones and zeros instructions that go into registers and all those super low level hardware stuff. And those are the kind of things that have to care. Do you have an AMD processor or an Intel processor? The interpreter has to care about that stuff because it needs to talk to the processor. So it is line by line interpreted into converted into machine code. Everything eventually has to be machine code, or else the CPU and GPUs can't do anything with it. This is not the same as this. This is confusing. If I'm priest, I don't show up to 331 lecture. Is that actually priest? Priest, are you here?
That's Joey.
Okay. Joey has already taken 116, and he would be confused by this probably. Sorry, Joey. And this is confusing. That is confusing. I shouldn't say it lightly. There's a lot going on there. We have an entire course on compilers at the 300 level. There's a lot, and I just did like 5 slides on it. I didn't do it any justice at all. I basically added that vocab word to your to your vocabulary is all I did there. Yeah, these are the lecture notes from last Wednesday that I never got to. I'm just kind of going back and cleaning house. All right, let's talk about RAM. We already saw a bunch of memory diagrams, so a lot of this is just like the motivating slides for the content you already saw. But this is RAM. A lot of you have probably seen this, or at least seen pictures of it, or understand that your computer has either 8 gigabytes of RAM or 16 gigabytes of RAM. Some of you have 32. You ballers out there with 32 gigs of RAM. And some of you, unfortunately, have 4. 4 is tough. By the way, if you have 4, I feel for you running in IntelliJ, because IntelliJ is going to take like 3 of those right off the bat. It's hard to run IntelliJ on 4 gigs. But this is what your RAM looks like. This is your RAM stick. And when we're drawing memory diagrams, it's literally, this is what we're talking about, is your RAM. Random access memory. This is, or we usually just refer to it as memory. That's what we're talking about. This is where both the stack and the heap live, is on your RAM sticks. One of those RAM sticks or across multiple of them. That's where your program's memory lives. And this is like a giant array. We also have hard drive. Memory is much, much faster than hard drive. We don't like going to disk. It's super slow. But we don't like paying for RAM. So we usually only have a small amount of this and a lot of that, because memory is way more expensive, but much, much faster. Even if you have a solid state hard drive, memory is much, much, much faster. Yeah?
What's the difference between a RAM memory and a solid state?
The difference between what? Sorry.
RAM memory and an SSD memory.
So SSD is going to be your hard drive, but instead of these spinning platters and mechanical arms, it's going to be no moving parts. It's going to be kind of like RAM, how it's all chips and circuitry, but in a, I don't know the technical differences, sorry about that, but it'll be like this, no moving parts, but made to be a lot bigger, a lot more storage, but it behaves just like a hard drive, but a faster hard drive, but not nearly as fast as RAM. Did that kind of answer your question? I don't really have much more than that. I can't go much deeper than the actual mechanics of a solid-state hard drive. I know it's more expensive and it's faster, but not nearly as fast as RAM. And there's no moving parts. So when we start our program, what happens is the JVM is going to talk to our operating system and say, hey, I need some memory. I got my user here trying to run a program. I need some memory. Operating system's going to be like, okay, I'll give you a chunk of that RAM stick. And that's what that program is allowed to use during its execution. And that's where we're getting our stack and heap memory from. Heap is a little more dynamic, we'll see in a second in today's lecture content. But we're going to get a chunk of that RAM stick, and that's ours to use. We're allowed to use that. That's going to be our stack memory. Now, our memory is like a giant array, literally. It's a giant array that's indexed by memory addresses. All those things that we only really see in this class on the heap. We say there's some memory address. We say OX whatever. That's a literal memory address. It's just like an index in an array, but it's in our RAM. This is just one giant array that's like 16 gigabytes big, large. That's what our memory is. So we get some chunk of that, some range, and then our stack is going to use up that range in a last in, first out manner. So we start with the first byte available in our section of memory. We start with the first byte available, and then we start adding values beyond that. We usually draw it from a top-down perspective. And we can only add values to the top of the stack, bottom visually, top conceptually, and we can only remove values from the top of the stack. Now when we draw the memory diagrams, we kind of just cross things out. But when we cross things out, we are actually deleting them from that array. And then when we add another value, so say we cross out a stack frame, the next thing that goes underneath that stack frame, which I don't think I had an example that does that yet, but the next thing that goes below that is actually in the memory address where that stack frame was. We're reusing that value. It's a little hard to visualize the way we do the memory diagrams, crossing them out. But we want to preserve all the history of your trace through the program. So we don't want you erasing things because it would be basically impossible to grade your quizzes. But that memory is freed up whenever we cross something off of the stack, and then we reuse that memory. It's a last in, first out, and we have no gaps in the stack. The values that we're using, the memory addresses that we're using, there's no gaps in there. We can only access we can only add to the top and remove from the top. Every method creates a new stack frame, and that's going to go on the top of the stack. There are a few edge cases that haven't come up yet. If we call a stack frame from inside of a loop, for example, we're in a dashed box and we need to add another solid box. The solid box goes way on the bottom underneath everything. We can only add to the top of the stack, bottom visually. We talked about code. I'm going to skip some of this because we talked about code blocks in depth last Friday. And I just verbalized all that. But what goes on the stack? Things that go on the stack are these things. These things. Doubles, floats, ints, longs, shorts, chars, bytes, booleans, and kind of strings. Strings technically don't, but we're going to pretend that they do. You can just ignore that I said that. In a future class, somebody's going to straighten that out and call me an idiot. Yeah?
What are chars?
They're characters. So if you have a single character of a string, it's a type char.
So like the letter A is a char?
Yep. These values of these types go on the stack. If you have any variables of these types, you declare a variable, it's going on the stack directly. Your int values, your bytes, they go directly on the stack. We'll really mess with ints and doubles and booleans mostly. They go directly on the stack. The values of them go directly on the stack. So what goes on the heap? Everything else. This is a comprehensive list. That's why I'm pulling out chars and bytes, even though we don't use those really in this class, and shorts, because this is a comprehensive list. If you have anything that's not one of these, it's going on the heap. And on the stack, we only have a reference to that object on the heap. If it's anything else other than these things, Everything else goes on the heap. So string is the only asterisk. This technically goes on the heap, but it behaves like it's on the stack. So we're going to visualize it on the stack because that's exactly the way it behaves, because it's immutable, but we're not going down that road. And when we actually run our code, JVMs, they update. There are different versions of them. They're very sophisticated. They're very advanced. They might do things different than the way we see them in class. When we see memory diagrams in class, we're going to show you conceptually how things work and how they behave so you can understand how your programs work. Technically, under the hood of a JVM, like for example, strings actually go on the heap, but that's a detail that we don't have to care about at this point. So our memory diagrams, Paul and I say they're about 80% accurate as to what's completely going on in hardware in our machines. And the difference is when we have the memory diagrams, your programs will behave that way. Christ. They will behave that way. So what we show you is going to be accurate to what you have to care about as a programmer. And then when you take a hardware course somewhere down the line, somebody might straighten you out and say, technically, we don't have to care in most cases, but technically this is what happened. And they can fill in the little details. In 116, we don't have to worry about every little detail, or else I'll just be talking about compilers and things like that the whole semester. Yeah?
I was going to ask where functions and methods are stored.
Where are functions and methods stored? And they're called, so they're stack frames on the stack, but where the actual definitions, like the code, I'm not going to have a solid answer for you, unfortunately, but there will be extra memory. So there's stack and heap. That's where all of our variables and all of our values are being stored. But there's also extra memory that the program uses for all the metadata, all the, like there's a class loader that'll load classes into memory in a separate spot. I don't know all the details on that. You'd have to ask somebody who's more into compilers, like Dr. Alphonse. He's the one who teaches that compilers course. He'll have an answer for you. But I only have like a surface level answer for you, unfortunately. All right, so now let's get to today's content. Where are we at? 2:30 already? It's 3:30 already? Christ. Okay. So these things go on the stack. Everything else goes on the heap. But what is the heap? So first, let's pretend we don't know what the heap is. And look at this short, simple little program. And try to figure out what this does in memory if we don't know that the heap exists, even though I'm going to draw the heap anyway. So let's see an example of, okay, we don't know the heap exists, and let's try declaring this list on the stack. Now the stack is a chunk of memory. It's a continuous block of memory, and memory is like a big array. So these values are actually one after another. There's no gaps between these. There's no extra bytes to fill in. It's literally that value, and then the next chunk of memory is the next value. It's very literal when we draw the stack. Those values are next to each other in memory on your RAM sticks. So let's pretend that this list goes on the stack. We're going to add 2 and 3 to the stack. We have enough room for 2 integer values on the stack. And then the next, 32 bytes here, 32 bytes, or bits, sorry. 32 bits here, 32 bits here. And then the next bit is going to be for the next value, which is x. Those are ints. Well, I didn't declare them explicitly, but 32 bits here, 32 bits here. Then we're ready for the next values. We can use up the next values in this big giant array, which is our memory. So what do we do on this next line, though? If lists were stored on the stack, we know we can do this. This code compiles, it runs, everything's fine. We can prepend 1 to this list and reassign it to the variable list. But how would we do this if we were to put this on the stack? If we said, you know what, screw all this heap junk, I'm just putting everything on the stack. How would we even do this? So let's look at a few options. These are bad options. Lists don't go on the stack. Of course, that's the punchline. I'll spoil it. Actually, I didn't show you a list on the heap yet. But if we put it on the stack, well, here's one option. let's just prepend 1. Put it right here. Move what was the head of the list, which was 2. Move that down 1. Then move 3 down 1. Well, this is a continuous chunk of memory. So we will run into X here. And we're going to try to put the third element of this list, that should say list of 2, the third element of this list in the actual physical location where X is stored. That's what we're trying to do here. Well, that's not going to work for us. Plus, it violates LIFO. This is why the stack X is a LIFO, last in, first out data structure. We can only add values to the end of the stack. We can only add values right here. The next value we add to the stack has to go right here. If we want to remove a value, it has to be Y, then X, then those. So this violates LIFO. It's slow. If we moved everything down, we could copy X down and Y down. If we have a gig of, you won't have a gig on the stack, but if you have a lot of values on the stack, that's a lot of moving. If you're doing this often, you're going to be moving values a lot. Slow, violates LIFO. All right, let's look at another bad option. Let's take the list, remove it from the stack, and then rewrite it at the top. We can write to the bottom, to the top, or whatever. Bottom visually, top conceptually, and again, this should be 2. And put those values for the list at the bottom of the stack. Well, we got a few problems here. We left a gap in the stack. That's no good. We copied the whole list. That's going to take a while. What if we have 1,000,000 elements in this stack? And we violated LIFO by removing something that wasn't on the top of the stack. Top conceptually, bottom visually. Yes, it should be list of 2. That is a typo. But at least my typo is in the bad example. That's not how computers work anyway, so I can just do whatever I want, right? These are just examples of what not to do. So I made that mistake on purpose, right? All right, but enough of that. Let's talk about what the actual example is. This is what actually happens in memory when we have a list and we want to prepend to it. So this is what we actually do. The good example, I hope I annotated this enough so anybody who's just looking at the slides for review knows that those previous slides were not how we do things. What we actually do is create this variable of name list. And the list that we create ends up going on the heap. And lists, specifically linked lists in Scala are linked lists. If you don't want to think about linked lists quite yet, don't worry, it's an LO4 topic. That's when we're really going to start testing you and teaching you about linked lists. But just as a foreshadow, linked lists are all over the heap. These values can be anywhere that they want, anywhere where we ask for the OS for more memory, for memory in the heap. Wherever we get memory, that's where the values of a list go, and they can be wherever. So to find the values for a list to actually be a list and be connected, each value is in a different spot in memory, and they know the memory address of the next value in the list. And then what we store in our variable is a reference to the first element of the list, which with linked lists we call it the head of the list. So we have a reference to the head of the list. The head of the list has a reference to the second value in the list, and the last value has a reference to nothing. We're going to denote it like this in the memory diagrams, and then in code, we're going to have it store null. The last value is going to have a reference, instead of actually storing a reference to a value, a linked list value, it's going to store a reference to null, which is nothing. So now we get to our last line here. We want to prepend 1 to the list. Oh, son of a bitch. That should be 1. I have a mistake in the good example, too. All right, I'll have to update the slides again. So now we're going to create a new value, a new linked list. Linked list node is what we're going to call them in LO4. A new linked list node at some other location in memory. That node is going to refer to the old head of our list, which still refers to the next value of the list, which refers to nothing. And then when we reassign to the variable, we're reassigning the reference to the newly created list, which is the newly created single element to a list, which refers to the old list. Don't worry, we will talk about linked lists for a full week later in the semester. But this is how we're getting around that. The punchline for today is that we're going to utilize heap space because throughout this line, we still only needed enough room to store one reference. We changed the reference, but we still only need enough room to store one reference on the stack. We don't violate LIFO. We don't leave gaps in the stack. We don't copy elements. We didn't copy an entire list. The original list remained completely intact. We didn't change it at all. We just added the minimal amount we had to do. We added the new value, which should be 1. We added the new value and updated a reference. Nice, clean, simple, efficient. We like linked lists. So heap space is much more dynamic. Whenever we need heap space, we want to create an object, we want to create a data structure. We go to the operating system or the JVM and say, yo, I need some more space. What you got for me? I need enough space to store an int and a reference to a linked list node. And the operating system says, yeah, I got you. And it gives us the memory address of where it gave us some memory. It said, this memory, you're allowed to use this, and here's the memory address for it. So we can ask for more memory, and we do that using the keyword new. New is saying, hey, operating system or JVM, give me some space. I need some space. And then it's going to give that to us. And then we do whatever we're going to do with that space from there, creating objects, storing state variables there, etc. And we only work with references on the stack. So the objects themselves are never stored on the stack. We just have references to them, which is the memory address of where we can find them on the heap. And this is what we call pass by reference. Since when we call a method, we're only giving a reference to that object to the method. Passing by reference, we're not giving it the whole object. And we already set an example where the method can change the object. We had a method that took an array, changed the array, and returned unit, actually returned an int, but made changes to the heap by getting a reference to an object on the heap. Whew. All right. Any questions on that? There are no pros for linked lists? Oh, no. Okay. And I wanted to get to this stuff. If I don't get to all of this today, we're definitely doing this on Friday. Let's get you started on this project. So I think a lot of you are still wrapping up Project 1, but a lot of you are done even with the application objective 2. So let's talk about this new project a little bit. So I'm going to go set up my project, git clone. It's a little different depending on what version of IntelliJ you have. It might be VCS and then git project from repository. I'm going to paste that URL I just grabbed from the doc. And I have my point of sale project. Yeah. As soon as this clones, the first thing I want to do is mark my source directory as sources root. Don't forget that step. Mark directory as sources root. Now close these things that keep popping up. And as soon as you clone this repo, you should be able to go to view, go to store, view, self-checkout GUI, and run that thing. Oh, I don't have an SDK set up. Sometimes that pops up. I'm going to click through that. I get an error because I didn't have my SDK set up. We're going to run this, and you should see the GUI pop up. It won't have any functionality yet, but you will see the GUI if everything went right. So we see our GUI. Doesn't do anything. This is our goal throughout the assignment, is to make these buttons do some things. That format's bugging me. I know I'm going to sound just like I'm making excuses, like I hear from students sometimes, but I swear that works on my other laptop. For some reason, it doesn't work on this. Maybe because I'm plugged into the projector, it's messing with my aspect ratios. That's what I'll blame it on. All right, so let's, the $sign should line up. But, so we have some starter code here, not much. In project 1, a lot of the structure was set for you. Not so much in this one. This is where you're getting more practice setting up the structure of a project. So we have an item class with a couple of methods, description and price. And self-checkout, which has a little bit more set up for you. Self-checkout, which has add item to store, number pressed, clear pressed. You're going to have one of these pressed methods for each button on the GUI. And whenever that button is pressed, that method is called. Number pressed takes an int, which is the number that was actually being pressed. Enter pressed, checkout pressed for all the buttons, And then we get a couple down here. Display string. Did I close the GUI? I did, didn't I? Display string. Whatever this method returns, the GUI is going to call this method constantly. Whatever this method returns, that's what's displayed right here. So this method always displays empty string. So I'm not getting anything displayed. There's none to display. And then items in cart. As you scan items, they'll start showing up here. Whatever shows up here will be exactly whatever your items in cart method returns. These are the only two ways to check the state of your self-checkout machine. So when you're writing tests, these are the two methods we want to call to make sure your self-checkout machine did the right thing. And a few methods that'll be more important later. I don't want to go through all of that because I'll end up talking too long about it. What I do want to do is start spoiling a little bit of test cases. So let's go to our homework doc. Can't quite get both of these on the screen meaningfully. And go to task 1. Task 1, it's going to tell me to create the structure of both the item class, and self-checkout. So I want to start thinking about my test cases for those. I'm going to have to write test cases for the item class in this items package. And it starts with a constructor that takes two values, a string and a double, representing description and base price, and a method named description that's going to return the description that was given to the constructor. So we haven't written any test cases for classes yet. So how do we make sure that the constructor is working right and that description method is working right? Well, let's find out. So we have a little bit of a start already that's in the repo as soon as you clone it. But it's going to have an error as soon as you comment it in. And maybe I should have just done this in the handout. But we're going to have this error in the item class because we don't have a constructor yet. So what we want to do is create self-checkout machines. We want to create items. And we want to start testing our functionality. We get an error because we have no constructor. So let's fix that. This is the only code I'll actually write. The description. I'll just call it base price. Two variables, and the names of these are not defined in the documentation. I just pick whatever I want for these names. And I'm going to change it. Base price, LOL. I don't know. And now I get rid of my compilation errors, but I name those whatever I want. So one very important thing for testing is that you can't access those variables in your testing because in Autolab, they're not going to have the same names as whatever you name them in your code. So we can't access those. So if we wanted to, come on. So if we want to test those, we want to test items description. I'm going to create a new item. I have the description here. Now, what is defined in our in the documentation is the description method. That's named, it's defined, it's a bullet point in the objective, in the task. That we can check. So what I can do is say assert the item's description is equal to test item. And I have pretty simple test, just 2 lines here, to test that the item is doing what it's supposed to do. So when we test objects, or when we test classes, we're going to create an object of that type using new. I'm creating a brand new item with some description and some base price. I'm storing a reference to that item, and then accessing that object's behavior to make sure that it behaves the way that I expect. So I want to see if its description method is going to return the correct description that I expect, which is the description that I gave the constructor. So this is how we're thinking about testing our classes. Create objects of that type, and then make sure they behave the way we expect them to behave. So I don't want to try, we can try to get through this. At least it'll be on the video. You can watch it through slower. No, I can't get through the whole thing, but I'm going to get through at least part of this. So when we want the self-checkout, what I want to do is test, at least for now, we'll simulate this test. We'll code up this test of pressing 472 and then making sure our checkout machine displays the correct value. So for that, we'll create test pushing buttons, pushing number buttons. We're going to create a new self-checkout machine. Doesn't take any constructor parameters. I'm not going to mess with items right now. That's the third example I want to do. We'll try to get that in on Friday. And I want to simulate button presses. Number pressed 7. I forgot what numbers I said. 472, just so we're consistent. So I'm going to simulate pressing 4, pressing 7, pressing 2. So by calling these pressed methods, we can simulate a user pressing buttons without having to run the GUI. We don't just spin up the GUI and worry about testing that way. We're just going to call these methods. And since the GUI is separate from our functionality, we're able to test without the GUI. So user presses 4, user presses 7, user presses 2. And what I want to check, what I would expect at this point, is for my self-checkout machine to be displaying, display string, should be equal to 472. So that's what I would like to check. And for my money, for my purposes, I like to check every step along the way. So I would do something like this. And check each step of the way. Okay, I started a new self-checkout machine. It's supposed to display empty string. Make sure it displays empty string. I pressed 4. I expect 4 to be displayed. I pressed 7. I expect 47 to be displayed. I pressed 2. I expect 472 to be displayed. Oh, shoot. I expect that to be displayed. I'll do another test on Friday, but we got to get to this lecture question. And once you're done with the question, you can go and have a great day, and I'll see you Friday.